So what we were doing was taking the imp language. Right at the beginning we defined the grammar, the syntax. What does an imp program look like? And now, in the last 2 lectures, I showed you how to take an imp program in a particular memory and work out what the answer is. And we build these trees. And the second coursework, you'll have lots of fun with that. You'll be pleased to know. But now we're going to move on to our other paradigm of languages, the language LAM. And what we're going to do is small step semantics for LAM. So, small step semantics. For LAM. Now it's small because we're not going to say, here's a program, there's the answer. We're going to say, here's a program, a little bit of computation will take you here, and then a bit more over here, and then a bit more over there, and you'll just carry on with incremental small steps of computation. So, in the next lecture we'll do big step semantics. Both are valid, both are reasonable, and how do you implement a large step semantics? Well, one possibility is a sequence of small steps. So, incremental little steps. Right, and we're going to use LAM. So remember the grammar for LAM is this language, the term, it was, if I can remember, there's a variable, there's a term, back to a term, there's a lambda, there's a variable, there's an arrow, and there's a term, and then just some simple stuff, there's numbers, and then there's just addition of terms. Okay, so we're using this language now. So the first thing is, I want to just check, are you all happy with what this thing is, this lambda? Is it clear intuitively what that is? No. Good. Thank you very much. Helps me. So it looks a little odd, but it's actually just shorthand. It's very convenient. It's shorthand so we can write it down quickly. We don't want to spend too much time on it. But if I have lambda x arrow t, what this means is it's just shorthand. It means the program that takes x as input and feeds it into t. So it's a program, you've done your Java, you've written your methods, and it says public, static, blah, blah, blah. And then it says you have the name of the method, and then you have parentheses, and then you have some input. And then you have the curly brackets, and then you have the body of the program. Well, the variables that are the inputs to the methods, that's essentially the same as the lambda. Take some input, and then the body is t. So it might be unfamiliar. It's very compact and short, and that can cause confusion at first. But the reason it's compact and short is just so that you can write lots of stuff quickly and get on with it and get to the important stuff. But its meaning is quite clear. Take x as input, and then feed it to t. It's just a method. I mean, it's not really a method, but because of what we do with it. But you can think of it, you've seen this kind of thing before. And now before we do the actual small step semantics, a little bit more on scope, it's important to realize. So, when we saw the language imp, when we had new, we saw that you can have new x equals something in, new x equals something in, and there are several different occurrences of x at the same time. And we need to be clear, when we see an x, where is it bound? Where was it declared? Or when you declare an x, what's its scope? What does it cover? And the same issue appears here. It appears everywhere. Again, if you write a Java method, and you say, my method name takes an x input and does this, inside this, you see your x. That's the scope of the variable declaration. Outside, you can't see that x. So that's the same thing here. So So things like lambda x dot x plus 5, that the program that takes an x and returns x plus 5 is the same program. Well, let's see. Is the program that takes x as input and returns x plus 5. So scope of x in so that means inside here, all the occurrences of x inside here are this x. When we get an input for this x, it refers to every single x inside this t. Or x in t are bound. So that's another technical word. They're bound by the x in lambda expression. Lambda. So. Okay. So all the x's inside here are this x. If you write it out in English, it all gets a bit wordy and a bit unclear, but it's intuitively clear. Every single x in here is bound by this x. So for example, if I write lambda x dot x plus 5 applied to x, or even better, lambda x dot, just to be precise. So inside this term, you see there are two different lambdas and there are two different x's. It's just like with nu. We saw this in the last lecture. You can have several nus, they can have the same x. And it's exactly the same problem with exactly the same solution. You just have to be aware that this x comes from there and that x comes from there. So if you see an x, you just trot along to the right, to the left, and find your lambda. Alternatively, start with an x and a lambda, and then the t that's associated, all of those x's are bounded by that t. So again, all the x's inside here are bounded by this x. So all the x's inside here are bounded by this x, and then all the x's inside here, that's this one, are bounded by this x. Not those ones, because they're bounded by this one. And so you also have to realize that the choice of this name doesn't matter. If I wrote new x equals 2 in x plus 2, that's the same as new y equals 2 in y plus 2. So similarly, if I take the program that takes as x as input and returns x plus x, that's the same as the program that takes a y as input and returns y plus y. And we'll see in the course of this lecture, we just have to be careful. If we're careful, it's not a problem. But we have to be careful that we don't mix up our scopes. We don't accidentally take an x that's bound somewhere and imagine it's bound somewhere else. And I'll point out examples where that happens. Okay. Time for a sip of Coke. So we've done reduction rules for imp, and they started off being quite simple, and they got fairly complicated. When we were doing the new rules, they got so complicated that I had to scratch my head when I was doing it live and think, oh, is this right? Is that right? So it's subtle stuff. Now, one of the nice things about LAM as a language, it's much smaller. Imp has blocks and commands and parameters and definitions and integer expressions and Boolean expressions, loads and loads of stuff. And all of those syntactic categories, they all have 3 or 4 production rules. So, I don't know, you've got 15, 20 rules and you must deal with them all. One of the nice things about LAM, it's much, much smaller. So it's much simpler to deal with. And we'll see that now. So. that you've just been doing, although it's about grammars, I slipped in the idea of what is called a regex, and that's what this is all about. So computation So that's the only rule you need to know. There are some more trivial rules which allow you to do computation in side terms. But that's it. Fantastically simple. Now I've got to explain what all of that means, but it's very simple. So that's a plus point. So let's go through all of that and see what that means. Okay. So this thing is just the symbol for reduces to. So we did big step semantics, we had the vertical arrow, and we talked about evaluates to. We just say this reduces to. So this term reduces to this term. Okay? And then this is a regex. So I introduced the term regex in the homework previously. A regex is just a lambda term applied to something else. So whenever you see a lambda term applied to another term, that's called a regex. Whenever you have a regex, you can reduce it. And you get a free tiny lesson in Latin, I think. No one's interested in Latin? Okay, so this is when you can do computation. So you look at your big lambda term, and you look inside it, and you think, oh, there's a lambda term applied to something else. That's where I can do computation. Okay, and what do you do? Well, I've told you this program means this is the program, take an x as input and then do t. And now we've got some input, s is the input. So we've got a program, this is like, take an x as input and then do t, and give it the input s. So not surprisingly, what do? Well, we can replace that with the program t, and whenever we found an x, we'll put s there. The reduction, intuitively, for those who still like English, intuitively reduces the program. So, oops. This part, which is the program that supplies s as input to the program that takes x as input and does t. So it reduces, oh, it's gone too high now again. So this is the overall program that supplies s as input to the program that takes x as input and then does t, and we can simply replace that with so it reduces this to the program t where x is replaced. I'm going to run out of space by s. So we replace all of that stuff by the program t, but we replace x with s. It's fairly intuitively clear. The reason I like doing things formally, mathematically, is I hate writing down all these words. It takes so long, it's so tedious, and I can always slip up and make a mistake. I hope to convince you that the advantage of writing stuff out like this is that it's shorter, it's simpler, and it's more precise. That's why this is not more difficult, that's why this is easier. Okay, So all we're going to do is do a few examples. So example reductions. I'll even write on the board. If I have a pen, which I don't have, can I use these pens, Stuart?
No.
I can. Well, maybe not. Right. No, of course not. Sorry, never mind. All right. So I better write that rule out again. Oh, I should say, here, this is meta syntax. This does not mean T square brackets S. This means T but with S, X replaced by S. Just to be clear. Okay, so let's do an example too. So let's say I had the program which takes X as input and returns X plus X, and I apply it to 5. So it's a lambda abstraction applied to something, so it's a regex. Hooray! So I can apply this rule. And what do I get? I get T, so this was my T, and there's my S. So I get T, but with the X replaced by 5. So I'll get 5 plus 5. No, that's not the whole answer. Like I said, it's just a step of the answer. That's why it's small step semantics. So in a moment, we'll also say how to get that to 10. But I'm just focusing on these redexes. I should say these are often called beta redexes. Okay, not very hard. You just replace the X's with the S's. Here's another example. Okay, so this is now another lambda abstraction, and it's applied to something, so it's a regex. So what do I get? Well, here's my T, there's my S, so I get T, so that's X plus Y, but now the bound variable was Y, not X, so I have to replace Y with 10. This is the program that takes Y as input and does this. I'm giving it 10, so this Y will become 10. So this reduces to X plus 10. So what I'm doing is giving you some examples just to check you don't fall. Yeah?
Does the line 5 plus 5, does that count as a regex as well?
Yeah. So 5 plus 5 going to 10, that's another reduction. Do that in a minute. It's not the most important thing, it's a bit dull. We'll tell you that later on. Okay, so I just wanted you to make sure that when I say replace X by S, if it's lambda Y, then you replace Y. If it's lambda Z, you replace Z. Might be obvious, but unless I say it, somebody will just always replace the X's with something, no matter what the bound variable is. Okay. Right. How are we doing for time? Who wants to have some more fun? I'll just write it out again. Lambda X and T. But with S, whoops, that reduces to T. Okay, so let's try some interesting ones. Let's do something. Lambda Z, shall we say? Lambda K. Z K. to 5 to 10. Okay, I'll put enough brackets in there so it should be clear what's going on. Okay, let's start then. Let's start at the back. So, can you spot any redexes inside that?
Z can be replaced with 5.
By what?
5.
5. Let's have a look. You've got to read the brackets here. I know it's a bit far away. So, let's have a look. So, let's have a look. Okay, so there's a lambda term. So lambda is equal to, so this is a lambda term. Okay. It's lambda k arrow z plus k. So that's a lambda term. And then if you see the next layer of brackets, this bracket matches this brackets. So then this is a lambda term. Okay. And as you say, it's then applied to 5. So hooray! We've got a lambda term, which is here to here, and it's applied to 5. So that's a redex. This thing is not a lambda term because it's something applied to something. It doesn't immediately start with a lambda. So there's one redex, and as you correctly spotted, it's this one. So we can use that rule. Okay, so let's turn next. What should we reduce this lambda term to? Okay, so let's have a look at the rule. That's what we do. So the rule says if I have a lambda x arrow t and I apply it to an s, I get t, but with s replaced for x. So there's my x, there's the bound variable, new colour. So we just match off the bits. There's the lambdas, there's the bound variable, there's the t, and there's the 5. Okay? So what we should do is replace t, so take t and replace x with s. So what's t again? It's all of this part, and s is 5. So what happens when I replace z with 5? So can you see this? So t is lambda x arrow z plus k, and s is 5. What happens when I replace lambda k? Where's that come from? Oh, it is lambda k. What happens when I replace k with 5? Can you see this?
Z with 5.
Right, so thanks, Stuart. You've just learned something, but you know all this stuff. That's not helpful. Please don't do that. Okay, so if I say replace k with 5, well, I just replace, sorry, it's not, replace z. The x is z. So I replace z with 5.
What was that now?
So I get, yes, lambda k arrow 5 plus k. That is straightforward. When you know, you just take it slowly. We're replacing, even though I said k, I know, when I replace z with 5, I just look inside here and I replace z with 5. Yeah?
Isn't that 5 out of scope with the z?
No, that 5. Sorry, it's out of scope of the z, yes, because this is the program that takes z as input, it's done this, and now z will equal 5. So the 5 is not in the scope, it is z. So I'm replacing z with 5. Okay, let's do another example. You know, I've done this for 40 years, so I think this is sort of straightforward, but I agree, maybe it's not. Let's do another example. So that was complicated because I thought, yeah, you're up for it. I'll put 2 lambdas in. Maybe I went a bit too far.
Wasn't there another redex in the previous example?
Oh, okay. Let's finish off this then. Okay. Right. So up here, there's only one redex. You see, there's something being applied to 10, but the something is not a lambda abstraction. It is a lambda abstraction applied to 5. That's why we've taught you all this parsing and all these grammars, because they tell you what exactly it is. You see, these brackets tell you, I'm something applied to 5. So this overall term is an application. Yeah?
But once you apply
Okay,
the 5...
but you see that?
Yeah,
Okay,
but once
so
you apply
then,
the 5,
I know what you're going to
can't you
say,
get...
and you're right, but I have to go slowly. So inside this term, there's only one redex. There are not 2 redexes. Now, when you do this reduction, so we replace this thing with this thing, I guess this overall thing reduces to this thing, lambda k, arrow 5 plus k, applied to 10. And so a second redex is created. So to answer you fully, there was only one redex in this term, but when you can do a reduction, you can create new ones. So then you have to carry on. So if we carried on, right, since you struggled, well, I've tortured you enough. Maybe I'll move on. So there's another redex. What does that reduce to?
5 plus 10.
No, not you. So it's lambda k, so it's a redex because it's a lambda applied to something. Cool. So that means we can do our reduction. We need to take the k, and inside here, replace the k with 10. So what do we get? Yeah, 5 plus 10. Which later on will reduce to 15. So this part, the thing we're doing now, reducing redexes, is mechanical. I'm always telling you that some parts of the creativity, when you choose your rule, in P and Q, should we reduce Q if P is false? That's creative. That's a choice. It's up to you. This is mechanical. Once you get the hang of it, you just trot it out, and it's very easy. Right. So I'm guessing this is about 1/8 of the course, so I'm going to try and get it lodged well with you. So a few more. Right, let's try and do... John Levi. Oh, gosh, come out, Johnny. Oh, did he draw that?
No, he drew a dog once.
Okay.
I like
I won't say anything. So how about T plus... Okay, so there's a term. It's a lambda abstraction. It takes an x as input. Oh, I'm sorry about this. For 30 years I've written lambdas with a Greek letter, and now I'm trying to remember to write it with a slash. Okay, so it takes an x as input and then does t plus, and then it's lambda x arrow 7 applied to 9. Okay, so your turn next. Can you see a redex there? So can you see a lambda term that's applied to something? Right. But so to see a lambda term, well, look for the lambda. So it could be here. So is this the start of a redex? That's a good guess. Next, what do you think? Hello? Yes, it is you, unless there's someone sitting in between the two of you. Is that, so it's a lambda, but then is it applied to something?
No.
No. So it was a good try. Could have been that one, but it wasn't because it's not applied to something. It's the production rule that's being used is lambda. It's lambda x arrow something, and you can tell that because I wrote these big brackets. So it's not applied to anything. So that's not a regex. But what about this? There's another lambda. Is this the start of a regex? So you need to go to the end of the lambda term and then, is it applied to something? What do you think?
There isn't an X, which is an X.
Sorry?
There isn't an X.
That's true. So that's interesting, isn't it? This is the program that takes x as input and returns 7. So there's actually no x inside there. That's correct. That's not quite the question I'm asking you. I'm asking you, is it a regex? In other words, is the lambda term applied to something? Yes, it's applied to 9. And you can see it from the bracketing. I've got this term applied to that term. So once you know to bracket your lambdas properly, and there's an exercise about that in the current coursework, then you just say, okay, I've seen the lambda, where does it end? Is it applied to something? So yes, it is applied to something, so we have a regex. Hooray! Right, your turn next. Now that we have a regex, we can use our rule. What do you reckon? So what's the t inside this regex? What is, actually no, let's go. First of all, what's the variable that's being taken as input? Yes. There's our regex. Oops. There's our regex. Another colour. Right. So the answer is yes. So the variable is x. And we can see it. There it is. So there's the x. So there's the x. What about the t? So your turn, right to the back. What's the t in this regex? No, the 9 is what it's applied to. So it's lambda x arrow t. Lambda x arrow what? You have a go. Lambda x arrow what?
I'm not sure.
Okay, well it's utterly trivial. Literally, read after me. If this is lambda x arrow t, this is lambda x arrow 7. It's lambda x arrow 7. So the t is 7. So yeah, the variable 7, t is 7. Okay, and also we need to know what's the s. So your turn. What's the s? 9. There can't be many other answers. Yeah, there's the lambda x arrow t applied to 9. Okay, so all we need to do is figure out what is t, but all the x's replaced by 9. So that's your turn. And there are no x's, so it's very easy. So what happens if I take 7 and I replace all the x's with 9? 7. So therefore, this thing lambda x arrow 7 applied to 9 reduces to 7. Eventually this will be like that, I promise you. As I say, look, take your input and replace all the x's with 9. 7. Okay. How are we doing for time? And of course, the overall term, there's a lambda x arrow t on the outside plus, so there'll be a lambda x arrow t plus this, plus 7. Right, so we're going to do one more example. This is really exciting, really cool. I promise you. Oh, I need to do 2 examples actually. And x arrow x.
Oh. What?
X plus y. So, I have to warn you, this is a trick question. I've dug a little hole in front of you. So, if you can avoid the hole, I'll be very impressed. Okay, so this is a redex. I'll tell you that. Because I've got a lambda term applied to something. Okay, so in order to calculate the redex, I need to write down what the bound variable is, what t is, what s is. After you've done a few of the examples, you know you won't need to write it out so slowly, but to get you started, it's helpful to just structure your writing and your thinking. So what's the bound variable? Where are we up to? Your turn. Yeah. So this is this lambda term applied to this thing. So it's a lambda term, so it's this variable. It's not y, because that's the lambda term. Okay, so the bound variable is x. Your turn. What's t in this example?
Lambda y
Yeah.
to x plus y.
Lambda y arrow x plus y. Okay. And what's s? Your turn.
Y plus 2.
Yeah. Okay. So, what is t? What's the answer? When we do the redux, t with s. Your turn. Oh, I'm glad I got you. You might avoid the trap. You look like an intelligent young man.
I think this is where I fail now.
What do you think it is?
See, does the y plus 2 get passed to x, and then that x gets passed further into the lambda term?
Yeah.
So then it becomes y to y plus 2 plus. No wait, sorry. Y arrow x plus y plus 2.
Right. Okay. Close. I'll tell you what. I'm going to do it naively, and we'll discover the problem. Oh, do you want another go?
I think I got it. Sorry. Because if you pass y plus 2 to x, so it just becomes y arrow y plus 2 plus y.
Yes.
Okay.
That's wrong. But that's a natural thing to do. And given what I've told you, that's what you should say, so you're following perfectly. But I have to tell you about the wrinkle, the little complication. You know, there's always a complication in life. Here it is. So, let's see what we did if we did it naively. We do exactly what you just did. We take this term and replace x with y plus 2. No? That's what I've said, isn't it? I've said, take the t and replace the variable with the s. Okay, so, what is it? We have lambda y arrow. Oh, there's an x. Let me replace it with y plus 2. And then plus y. Right? Now, I have to stress, this is wrong. And let me tell you why it's wrong. The problem is that, you see here, this y, right, that's bound to that y. Yeah? Remember all that scope and stuff? That means it's not really y, it's just take the input and do x plus the input. And that's okay here. That's still maintained. Take the input and, plus the y, that's the input. But this y, which comes from this y, from the y plus 2, which comes from this y plus 2, which comes from here, this is not that y.
Paper gun.
Oh, thanks. Can we do that again? Oh, I can do it here, can't I? This y, which comes from the y plus 2, comes from here, which is the s, which comes from here. So this y is nothing to do with this y. This is a bound y. And it only affects this y. This is a separate y. But suddenly this y will now get bound by this y. So you have to be careful. If you're substituting under a lambda, you cannot capture these free variables. So, what you need to do is, when you look at, if you're substituting into a term and you bind a variable that's inside here, you should change this variable. Remember I said this is the same as lambda z, arrow z plus y? Sorry, lambda z, arrow x plus z. So you're unlucky, there's a clash here. You're unlucky. Usually you don't get clashes, but occasionally you get clashes. If you do get a clash, you should change the name of this variable. So the answer is, it's wrong as this y becomes bound by this lambda. So the simple solution is just to avoid the clash and change this one. So that could have been lambda z, arrow x plus z, and then the z's and the x's are different, and there's no problem, and you can just do replacement. So, had this been the z, so I know to worry. See, I knew what was going on all along. That's because I built the trap. I knew that there's a y being bound here, and there's a different y there. And when I replace this x by this y, it'll bind this y. So, when you can spot this, when you know it's going to happen, you can just change it. So let's call this lambda z, arrow x plus z. So had that been the case, it'd be lambda z, arrow, and then the x gets replaced by y plus 2. And there you get the correct binding. So again, if you say it in English, it takes a long time to say it. But it's actually just formalizing some intuition. When you write a method name, the variable name doesn't matter. But if you've got a method with a variable involved that's bound, and you put some global input into it, you can't get it bound locally. So you have to be careful. So when you're doing the replacement, just check. So the moral of the story, check in T if there are variables bound that also occur in S. If so, rename the bound variable in T. So, this is a slight warning. Everything else is fairly straightforward, you get the hang of it, but that's the place you might trip up. Okay, that's a good place to stop. So if